Hello, welcome to the lecture on polymers. In this lecture, we will look at liquid crystalline polymers, and this is an interesting state which we have not discussed so far, where there are liquid like characteristics, but there is crystalline order in the liquid like system. And of course, we are familiar with liquid crystal displays. So, in small molecules and in inorganic systems, liquid crystals are well known, but we also see that along the macromolecules there can be small moieties or small segments which can have liquid crystalline order. So, therefore, in polymers also we can have liquid crystallinity. Just to remind you that this week we are discussing polymer materials of different kind. We will look at copolymers and blends and composites as we look at the use of polymeric material in all different applications. And so this lecture also we will focus on some of the key uses of liquid crystalline polymers. These are materials which are used in small quantities compared to the overall polymers usage, but given the advantages they provide, it is used in niche applications. So, we will look at these liquid crystalline polymers, but by first looking at what is meant by the liquid crystalline state, and then look at few examples of some commercial materials and what gives them liquid crystallinity. And in the end we will also see, given that we have rod like segments in liquid crystalline polymers, how can that be exploited in polymer processing to orient the rod like segments. And so, liquid crystal are materials where there is a liquid like motion of molecules, but at the same time there is solid like ordering. So, here for rods or discs the ordering is clear. For example, with the arrow which is shown here, you can clearly see that there is an orientation which we can assign for the disc or for the cylinder. But what is crucial about this state is the fact that there can be exchanged between these rods or between two discs. So, therefore, what is translational motion of these entities is possible. However, orientationally they remain more or less fixed. So, in this case the director vector, as it is called, is pointing to to one particular direction. Of course, we could have a liquid crystalline order in which the direction could be different in one place and it could be different in another place, and within these domains there is exchange of molecules which are possible. So, you can read a bit more about these liquid crystalline material and how there are different types of liquid crystalline material depending on whether it is a solvent which leads to the formation of liquid crystalline order or disruption of it, or whether it is related to temperature. So, these are textbook related information on liquid crystals of small molecules. Now, given that we are looking at a macromolecule in this course, what we are looking at those set of macromolecules where in parts there is rigid rod like moieties. So, now what can happen once you have this kind of a system is the fact that some amount of ordering can take place between these rigid entities. And so, just the way we drew a director vector for a small molecule liquid crystal, now these segments of polymer chain can align themselves, and therefore, we can again look at a director vector. So, these small groups which are present, which prevent bond rotation or which are leading to chain being rigid locally are called mesogen. So, depending on what kind of macromolecule we have, we could have mesogen along the backbone the way it is drawn here, or it could be as a branching point, or it could be as a side chain, and so on. So, there are various possibilities of liquid crystalline polymers. Also the ordering is of different type, and again you can go through and familiarize yourself with nematic and smectic, and in fact if you do just an image search, you will see beautiful pictures of how some of these materials can organize themselves in variety of different ways. Of course, liquid crystal given these kind of arrangements have very interesting optical properties, and that is why liquid crystal displays, and there are so many products which are related to optical properties of these materials. In case of polymers though, we will see mechanical performance is what is the biggest advantage. So, the liquid crystalline polymers can have the mesogen along the main chain, or they can also have in between a spacer. So, we can have mesogen which is rigid rod like entity, and then in between there can be spacers. So, for example, if there is a copolymer of ethylene and other components, then the ethylene component will be flexible and the other components will be rigid. Given our discussion so far, can you try to guess what would these other components be? What kind of bonds along backbone might make the chain more rigid or less flexible? And if you think and recall some of our earlier discussion, if you do not have single carbon-carbon bond along the chain, that will immediately start leading to some amount of rigidity in macromolecular chain. So, couple of slides down, you should not be surprised looking at the groups that we will see which are part of the mesogens. So, therefore, mesogens can be on the side group, they can be a cross-link polymer can also have the liquid crystalline mesogens on them, and generally these are fairly high cost specialty applications kind of material, but given their requirements, let us say in electronic industry or aerospace applications, we use some of these materials. Of course, Kevlar is the most prominent example of these kind of liquid crystalline material, and we also have polyesters, of course, are a very common material used in variety of applications. We also have liquid crystalline polyesters which are quite common. So, we will look at them. Before we go on there, let us just look at thermodynamically what it means to have this liquid crystalline order. If we look at the free energy change for this transition between disordered mesogens of a macromolecular chain. So, I am not drawing the overall macromolecular chain, but you can understand that this is part of, let us say, a macromolecule, and then we are looking at the rod like segments ordering themselves. So, you could have an ordered state, or you may have a disordered state. And so, in both of these cases, so this is a disordered state. So, we are when we look at the transition, we are looking at from disordered state to an ordered state. And so, the Gibbs free energy change for this as we know can be thought of as two different components. One is related to enthalpic component which is based on interaction between macromolecules, and the other one is related to the entropic component which talks about the ordering as well as the number of different ways in which these macromolecular segments can be positioned with respect to each other. So, therefore, depending on the macromolecule that we have and depending on the kind of steric hindrance that is present or in these organization of rigid entities, we will have differences in terms of the entropy. What we have, as I mentioned, is there is exchange possible between different segments. So, this can diffuse, and so therefore, they can change place, but the overall orientational order remains fixed. So, macromolecular chains and especially the red part here can move around, and because of that the rigid mesogens can also move about while still maintaining their orientation. And of course, in this case they are all randomly oriented in any case, and they will continue to be randomly oriented even if the red segments move. So, therefore, the alignment when happens of these mesogens, that leads to a decrease in orientational entropy, because instead of these being oriented randomly, they are all oriented and in one direction. But at the same time, translational entropy is still possible. So, therefore, high degree of translation entropy is retained, and this is the liquid like character. So, we have a solid like character which is orientational entropy being lost, and we have translational entropy still being high, which is a liquid like character. So, molecules and mesogens in this case can exchange places and they can diffuse around. And so, the influence of this orientational order is on very high modulus and strength. So, therefore, very good mechanical properties. The other feature that ends up being attributed to these polymers is because of this orientation, anisotropy comes in. So, the properties in one direction, so in this direction are going to be very different compared to properties in this direction. Of course, in a bulk sample we may have many such domains and they are all randomly oriented. So, in that case the overall bulk sample still may be isotropic, but we will see at the end of this class that how we can try to purposely orient most of the liquid crystalline order, especially let us say in a fiber. When you have a fiber and if you want all the orientational order in the fiber direction, we can get a very strong fiber if we do that. So, therefore, this orientational order is exploited for achieving very good mechanical properties. Now, over and above this entropic considerations of organization and assembly of these mesogens, we also have molecular interactions, and of course, these molecular interactions could be in the form of hydrogen bonding or in the form of pi interactions. We will see that variety of these mesogens and rigid rod like entity will have benzyl groups, and so therefore, there is pi-pi interactions or stacking possible. So, a benzyl group can be thought of as a disk, and therefore, disk can stack as we just saw. So, therefore, these interactions are important also. So, the overall Gibbs free energy for whether liquid crystalline order will occur or not will depend on both of these factors. However, one thing we need to keep in mind is the enthalpy of crystallization for disordered to ordered liquid crystalline system is much less compared to a crystalline melt to crystalline order that we already discussed in 17 and 18 lecture earlier. And that is because the orientational order is only present, translational entropy is still present, and therefore, there is flexibility of molecular motion. While in case of a crystal, what we saw is there will be a folded chain crystal, and of course, this will be only vibrations around mean positions is permitted. So, therefore, this is a perfectly solid like material, while what we have in liquid crystalline cases is still liquid crystalline order present. And so, the overall energy change when we go from random to liquid crystalline order is much less compared to a melt to crystal transition. So, now let us look at some of the commercially available examples of these, and just to compare let us look at polyethylene terephthalate. So, the ethylene group of course gives it the flexibility, but we also have the terephthalic acid associated group, and so polyethylene terephthalate of course has a glass transition temperature of 75 to 80 degrees Celsius, as opposed to polyethylene which is in minus 60 to minus 80 degrees Celsius. So, therefore, PET already has molecular rigidity much higher than polyethylene. However, still because of the polyethylene groups, CC bond being present, bond rotation around that is possible. Now, instead of these, if we look at other polyesters which are commercially available, and here there are two examples of it, you can see that now we have the same way bulkier groups along the backbone, and also we have ketone linkages which actually will prevent any rotation. So, that is the key to get liquid crystalline order. So, this molecule has lot more rigidity compared to the ethylene segments that are there in PET. So, therefore, we have polyesters which is PET and polyester which is let us say Sumika Super LCP or RTP LCP or these Vectra and Zyder, and the cleverness here is in terms of introducing mesogens or rigid entities along the macromolecular chain using similar chemistry of forming basically acid and alcohol reaction to get polyesters. So, one of the key feature in summary is to say to basically avoid the carbon-carbon bond rotation and then presence of bulkier groups along the backbone to improve the chain rigidity. So, now just to give you how much difference does this make by just introducing these mesogens, and in this slide I have taken commercially available data based on PET and liquid crystalline polymer, just to give you an idea of how much difference does it make. and this is a slightly complex diagram. So, just spend some time looking at what is being tried to say. So, we are looking at 3 different properties: tensile strength, tensile modulus and strain at break. So, and we are looking for 2 different materials: PET, PET bottle, PET, and then liquid crystalline polyester. And let us look at tensile modulus first. You can see that the scale goes from 1 to 100, and then of course, this is 200 also. So, you can clearly see that the LCP polyester has higher modulus compared to PET. Similarly, you can see tensile strength of PET is less compared to the LCP polyester, and this is a logarithmic scale, by the way. So, the difference between the two is quite huge. It is more than 3-4 times some of these property changes. But on the other hand, if you focus on strain at break, you can see that strain at break for PET is much higher. So, clearly therefore, the PET is less stiff, it is less strong, but it is more flexible compared to the LCP polyester. You can also look at the thermal response of it, and we have already seen that instead of looking at glass transition temperature as a transition, many engineering applications people look at the Vicat softening point or the heat deflection temperature, and in both cases you can see that the PET is much less compared to the transition points. You can see here the difference if so this is 200 and this is 400. So, you can see what the deflection temperature increases by 200-300 degrees Celsius. So, that is the advantage that you can get by introducing liquid crystalline order in a material, and while processing you introduce this order and then bring it below glass transition temperature, and now because of that order which is present in the sample, the mechanical properties get a tremendous boost. The thermal stability of the sample also increases very significantly. So, that is why you can see the other claim that I made, that even though these materials are expensive due to the chemistry and processing of them, they are still used in fair number of niche applications. And Kevlar, which is the most commonly known and popular example because of its spectacular properties, is useful because of this liquid crystalline order. And basically its properties are extremely high. So, there are different grades of Kevlar which are present, and property can be as high as 130 gigapascals, and more importantly its specific strength. And by specific strength we mean the strength or any mechanical property per unit mass, per unit weight of the polymer. And you can see that in aerospace applications this will be such a premium quality to have, that if your specific property is very high, which means you need to use less of your material in terms of mass, and which is the key characteristic for a material being very light and useful. So, for metals, for example, this is around 100, but for Kevlar it is 2500. So, there you can see 25 times specific mechanical properties. And the temperature range for long term use in air is also very significant. So, you can use, for example, in a variety of applications where temperature can be as high as 150 degrees Celsius. So, just to let you know that since as polymer scientists and engineers, this is one of the successful examples of manipulating molecular level details to achieve spectacular performance. And so, aramid you can look up and try to see which family of polymer does it belong to. Is it a polyether, is it a polyamide, or is it a polyimide? And the other thing about Kevlar, and this is taken from the commercially available data sheet as to how you can exploit this liquid crystalline order during processing to organize the order, and then once we bring it below glass transition temperature, the order gets frozen and we have excellent mechanical properties. So, in case of Kevlar, if you notice these groups, you can answer the question which is there on the previous slide, and the key feature here is these hydrogen bonding between these moieties. I am not going to take the name of these moieties because I want you to think about the answer on the previous slide, but you can see that basically there is a stacking of these chains because of these strong interactions between different chains of polymer. And so you can see that there is therefore an orientational order which is present. So now if you look at any macromolecular system, and if let us say it is a flexible macromolecular system, in dilute systems basically there will be macromolecular orientation in all random direction. Even if you increase the concentration, the randomness will remain, and if we now extrude this polymer out of a narrow opening and then if we stretch it to make a fiber, let us say, then what we will end up getting is of course partially extended chains. And this we have seen orientation of macromolecular systems we looked at in quite a bit detail in lecture 20. And now instead of this flexible segments, if we have rod like segments. So in case of dilute solution also these will be present, but randomly organized. Even when we increase the concentration, there will be some tendency now, because of the concentration is too high, instead of them being crisscrossing each other, there will be some tendency for them to start ordering themselves. And if you now do processing where you try to extrude them, spin them through a very narrow opening and also then stretch them. So then what happens is you will get a perfect fully extended orientational order. And so this is what is the key to the performance of Kevlar and variety of other liquid crystalline systems. And so with this we will close this lecture, and I am sure all of you have already narrowed down what family of Kevlar does belong to. Thank you.